will talk about delays in the System Dynamics Summer School. Things take time. In reality, also in your model, and in System Dynamics, stocks take time. Today, in this lecture about delays, the learning goals are to know the different types and orders of delays and how to recognize their effects, and also in addition to this, how to implement them into your model. Well, as you might have understood, there are two types of delays. There are material delays and information delays. Information delays are often called in System Dynamics software smooth functions. And at the same time, there are different orders. Theoretically, there is an infinite number of delay orders, but in practice, the first order, the third order, the pipeline or infinite number, and an nth order, which is a custom delay, are most often used. I would say in this order of appearance, so the nth order you hardly see, but the first order and the third order are often used. Now, in principle, or actually by definition, this is the first order delay. We have a stock with an inflow. The inflow has any value which you can give it, and the outflow is defined as the stock divided by the delay time. This is by definition a first order material delay. The behavior of a first order material delay is as you see. You can define this both with a function, so you see the function here in the case of VenSim. You see that it's an if you use the function, it's an inflow, the delay time, and the stock divided by the delay time as the initial value. And the behavior is the same. You have a similar function, delay 1, in Stella, where the initial value is optional. Now, if you give a step function as an input to this function or to the structure, then you see that they behave exactly the same. This as intended. So you see that there is a delayed, first order delayed response to the step function, and the average delay time is, well, probably somewhere here. Now, an information delay has a slightly different structure, and by definition it's defined as follows. So we have an input and we have a net flow. The net flow is defined as the input minus the stock divided by the delay time. So instead of having an inflow and an outflow, we have an input, we have a net flow, and we have a stock. And the delay in this case doesn't go from the inflow to the outflow, but it goes from the input to the stock. So if we define the output as a smooth I function in VenSim, or smooth 1 in Stella, where the input, this needs to be the delay time and the stock, are defined as inputs, then it will work the same. So I'll correct this. Then this needs to be in input. Always beautiful. My students in Delft love it when I do this. Now let's continue, and I'll switch back to the later pointer. Again, we see that the function and the structure, so the hard-coded structure and the function, have exactly the same behavior when they're fed with a step function. Now, it seems that they are the same. What are they? And it's interesting to know under which circumstances they're different. And there it's very useful to observe the different structures. So we have the inflow and the outflow, where actually the delay time, so the outflow is divided as the stock divided by the delay time, and we have the input with the stock here. Well, what you might see is that in this case there's conservation of mass, and in this case there's no conservation of mass. Here you delay from the input to the stock, and here from the inflow to the outflow. So those are the different things. And you see that there are only two things, and if we have the same inflow as input and the same delay time, then it's interesting to know what happens. Now, in this case we have a static delay time, so the delay time is 10 in this case, as you might have inferred already, and you see that they behave exactly the same. Now, if we have a dynamic delay time, where the delay time drops at t is 15 till 5, then we see that something strange happens. The information delay does roughly the same, but the material delay behaves differently. Now, if we go back or we go further, we see that this is very logical. Because in here we have a stock and we have an outflow and a delay time. So imagine, for example, this is a stock of goods in a harbor, and the harbor control smoothens their process, cutting the throughput times in the harbor. At that moment, what you'll see is that the outflow temporarily increases to deal with this shorter delay time. Well, in this case, of course, that cannot happen because the stock is not emptied all of a sudden. So you see that there is a slight increase in how fast it sort of moves to the asymptote. However, there's no big jump. So what you see, and that's also why this one is called smooth and this one is just called delay, that they behave differently. And that's only when we have dynamic delay time. Now we also have higher order delays, and that's when we put a couple of these things next to each other. So for example, in an aging chain. An aging chain is essentially a higher order material delay. So we have an inflow, we have a flow, we have an outflow, we have two stocks. So in this case, the delay order is 2. The number of stocks determines the delay order. And if we do this the same with an information delay, we use the stock 1 as the input for the net flow 2. And the stock 2 in this case is the second order information delay of input. And the outflow here is the second order material delay of the inflow. And again, they behave very similar to the first order delays. However, as you can imagine, because this one only reacts to this one, to the output of this one. If we have this step function, you'll see that this one ramps up later. So we can even create even higher order delays, and every stock in such a delay structure again counts for the order of the delay. System dynamics software packages have built-in functions for these delays. So generally for the first order and third order delay, of course the fixed and pipeline delays, so the infinite orders, and also for the nth order. Now in this case I made a couple of different responses. So the blue one here with the 1 is the first order delay, and you see that it starts immediately. With the second order delay you see, so that's the purple one, you see that it ramps up a bit later. And with the third order delay, which we often use, it ramps up even a bit later, so you can get some sort of S-shaped behavior here. Now, the higher we increase the order, so for example to 100th order, you see that it, so I need quite a small time step by the way to do that, we see that it's almost similar to the delay fixed, the pipeline delay, which is exactly the same behavior as the input, but a bit later. So in this case you see that the delay time is 20. And you see that the 1000th order, so that's I use the delay n, is almost the same as the pipeline or fixed delay. So here you see it in a larger scale. You see that the number 6 here is almost the same as number 3, but not yet. So you see that you need really high numbers to get really this effect of the infinite order. Now, when I'm assessing this for my students, generally what I do is I give them a variable input and a variable time delay, and I give them a graph like this, and I ask them, so please give me the different orders. And here you see all possibilities. If you have a first, third and a pipeline delay, and you see, okay, we have directly ramping up the first order, starting a bit later are the third orders, and starting only, in this case you see that the initial time delay is 10. So at 10 you see that the pipeline delay does its job, but as soon as the time delay here changes, you see that these things in this case becomes bigger, so the output becomes smaller, but only for the material delays and not for the smooth functions, so not for the information delays. So here again you see what happens. So now you can distinguish that these are material delays and the other ones are information delays. So now you know which one is which. Now here we can try that again. So I'll leave this to you yourself to try this out. So you can just pause the video. Let's see what happens, and try this out. Now, if you want to implement these delays in your models, this is a structure I frequently use. I call this a procurement delay structure. So we have, in this case, production capacity of fossil resources, so let's say oil rigs and stuff like that. And we have a planned capacity for these resources. They're decommissioned, the planning happens, and also the commissioning when they become online. And between these I put a third order delay, because there are different steps. For example, you need to get a permit, you need to get the building materials, all kinds of things which need to happen. So first order delay, where it would ramp up immediately, wouldn't be realistic. A higher order delay is more realistic. So in this case, a delay 3 is doing a better job than a delay 1, especially if you have a very discrete input here. Of course, if this input is very continuous, you will hardly see any difference. So this is a way of including a delay in your model. The conclusion of this story is: use delays when necessary in your model. They change the behavior of the model, and they are essential to what you try to mimic, which you observe in reality. The delay functions are created to create a simpler model, so you don't need to hard code all these delay functions, especially when you have higher order delays that can get quite messy. And think about the delay type and delay order, when to use which. When do you need a material delay? So that's when you have conservation of mass or energy or whatever. Conservation of stuff. And an information delay or smooth when there's no such thing. So that's basically just averaging over the delay time. Also think about the order. Is this a first order where you have an immediate response? Is there a delayed response, or is it fixed? Word of caution, because the delay fixed in both packages where I checked it, so both Invensim and Stella only react after the initial delay time, it doesn't seem very realistic. So your model basically needs startup time to make use of delay fixed. So I would generally try to avoid using a delay fixed unless you really need it. Often, for example, when you want a response to last year's price or something like that, a delay 3 will do exactly the same. Think about this: if there's a huge price change, you'll generally react faster than when the changes are more gradual. So using delay fixed, where you really have to wait till the year is passed, that wouldn't really make sense. Now, for exercising with this theory, what you could do is use the theory exercises of the Delft Method book, which is available to you. I would recommend exercises 5.2 and 5.4 because they're very difficult and that's fun to try out, but all other delay exercises as well. The delay exercises which are similar to the ones I showed on these slides. And try building the COVID-19 model, so that's exercise 5.8. It will take you a bit of time, but it's very useful to see how these delay functions can be used, in this case in the SEIR structure, so a structure to simulate the development of an infectious disease. Good luck with this, and I see you in the week where we discuss whole theory and everything. Goodbye.